And first thing we'd like to look at is the site information. So our target area is the city of Santa Clara. From westbound is about Lawrence Expressway to the right, approximately Santa Clara University, and south from Stevens Creek to a little past the 101 freeway, as you can see on this little picture here. And since we're looking at the traffic system, we deduced that there were some current traffic problems that were present right now, and we've determined these to be congestion, long queues, and the potential lack of efficient emergency response.
Given the problems that David just noted, we wanted to create a model that could be used as a traffic management solution for the city or the county. We wanted to create a model that could be used to help alleviate day-to-day traffic issues as well as something large-scale, like an evacuation, which we'll show you. And also, as far as environmental context, reduced delays equals less driving equals less gas consumption and lower carbon emissions.
So these are the objectives of our project. And first of all, we would like to accurately model the city of Santa Clara's traffic network. Second, we would like our model to be flexible and can show different effects of proposed changes implemented on this model. And finally, we hope this model can help us derive initial solutions for problems of different scales, ranging from a small-scale lane closure to something such as a whole citywide evacuation.
So now we're going to strategy and design. So here's our basic project scope. The main goal of this project, as I said before, was to develop a traffic model for the city. This would include signal timing plans, an origin and destination table that accurately reflects day-to-day traffic in Santa Clara, and it would also include accurate geometry of highways, expressways, arterials, and a few collector streets. We would then test the adaptability of our model by creating different initial scenarios and determine problem areas from the scenarios we create, and then we'll formulate solutions based on those.
So here's a basic snapshot of our model, as you can see in this picture to the right. The program we use primarily was called Quadstone Primix Modeler, and with our model, it realistically simulates traffic conditions, and it's able to collect various types of data from the simulations we run, such as travel time, delay, mean speed, etc.
So as far as design strategy with building the model, we began with the geometry. We overlaid images from Google Maps and Google Earth to get the layout. And then we were able to obtain select signal timing plans from the city of Santa Clara. What we couldn't get, due to the fact that some intersections are operated by different jurisdictions, such as the county, we went out to the field and timed them ourselves. The OD table we were provided by our professor, Dr. Ha. However, it was a very old origin destination table, so we morphed it a little bit to create a more realistic representation of what we believe is the city's traffic. Also, for testing, all of our simulations ran between 30 minutes and an hour.
So some of the resources we use, aside from Primix Modeler, as I stated earlier, we also use Primix Analyzer, which helped us quantify the information we obtained and helped us develop our charts and graphs. We use Synchro 7 primarily for our signal timing as well as signal retiming. And as Jake said earlier, we use Google Earths and Maps to help create the accurate geometry of our system. And once again, we use field data to obtain the signal timing plans that we were not able to obtain for the city.
So here's a video of our simulation. Here's the extents of our traffic network. We're going to be zooming in now to the 101 and Bowers intersection. Right now we're running what we consider to be our base simulation, which is simulating average day-to-day traffic. As we move down the 101, the green lanes mark high occupancy vehicle lanes, which we were able to implement along the 101 and Santa Tomas Expressway, Lawrence Expressway, and Central Expressway. This base simulation, as well as all of our other simulations, uses the shortest path algorithm to determine routing for the vehicles between each origin and destination. This is the De La Cruz Colon interchange. We just wanted to show that because it shows the attention to detail that was put into the geometry of our system. Lastly, this base simulation, which you're seeing now, is our standard of comparison for all testing that we will show you in the future. from the space simulation, we were able to gather some data over an hour. We were able to obtain average vehicle mean speed for the hour. The average vehicle, averaging all the vehicles in the system, the average speed was 28 miles an hour. This might seem low, but it's taking into account the fact that cars are stopped at intersections, they're turning, and they're slowing down. The average vehicle mean trip delay that we gathered from this model was 286 seconds. So that means the average car is experiencing 45 minutes of delay in a given trip.
So now we'd like to go into testing and application of our model and show off kind of what our model can do under different circumstances. So we wanted to look at three main scenarios: a medium impact case, an extreme case, and a low impact case. As you can see here, the medium impact case, we closed Santa Clara Expressway, all lanes in both directions between El Camino Real and Homestead. For our extreme case, we did like a pre-flood evacuation scenario in the event something like an earthquake followed by a flood may affect the city. And we addressed the low impact case, which was a lane closure along Central Expressway between Bowers and Lafayette. However, we did not perform a full analysis because after we looked at this and looked at the citywide impacts, it was not that great. So we decided to spend our time mostly on the medium impact case and the extreme impact case because we thought they would be of greater importance.
So as David said, we're going to show you our first application of our model. This is what we consider to be a medium impact case. We're closing Santa Clara Expressway from El Camino down to Homestead. Both ways. We thought this would simulate major construction or blocking off the road for some sort of special occurrence.
So one of the analysis we did was a travel time analysis. We looked at all of the origin-destination pairs in our system, and after we implemented the street closure, we looked at how many of these OD pairs had an increase in travel time. As you can see from this table, we saw that there was a 30% increase of these OD pairs that had an increase in travel time, therefore showing that this street closure is indeed affecting our system.
We also ran level of service testing for different corridors surrounding the blocked off street. Here you can see LOS testing. The program takes it at 5-minute intervals. So we ran LOS testing for El Camino between Kylie and Scott, as well as Santa Clara southbound approaching the closed off road. As you can see, there's a lot of F's up there, and that's largely due to the Santa Clara and El Camino Real intersection. We also ran LOS testing for Scott between El Camino and Homestead, and the main problem here is surrounding Scott and El Camino Real.
So now we're trying to figure out what kind of solution do we want to implement. So what we decided on doing was doing a new signal retiming plan. You can see this here below. We created this using Synchro 7. However, to get this data and to get this signal timing plan, we installed loop detectors in our parametrics model to take vehicle flow, so we get a number for vehicles per hour. We plugged that into Synchro, used the optimizing thing, optimized it, and was able to generate this new signal timing plan. Just a further thing to note that if there was still congestion and these two intersections of retiming were not enough, we would propose retiming other intersections around the area, also possibly doing lane configuration changes, such as adding more left turn or right turn lanes, and the possibility of adding variable message signs to warn drivers of what's coming ahead. We also did a travel time analysis for this, and we looked at the number of affected OD pairs from the problem case with the street closure, and we saw how many of these OD pairs saw a decrease in travel time. So we noticed that 76% of these pairs had a decrease in travel time, thus showing that our retiming plans are actually helping the system and helping to get cars moving along at a little better rate.
We also reran the LOS test for all the corridors we analyzed in the problem scenario. And the solution, which is marked in the blue columns, overall we saw a general improvement in LOS for all the corridors, especially here surrounding the intersection at Santa Clara and El Camino Real. Similarly for Scott, north and southbound, we saw general improvements. The main issue here, where you see all the F's, is that we have an internal zone that's generating cars. So it's pointing out a lot of cars onto Scott, cars that would normally go onto Santa Clara. So that's the reason for that hitch.
Now we like to go into our extreme case, which is our pre-flood evacuation scenario. In this one, we had to completely change the OD tables to reflect people exiting the city. And to do this, we got floodplain data, and we were able to use this to help us determine the direction people were traveling. So we also did a travel time analysis for this, and there's actually a less number of OD pairs because everyone is going from one direction of the city to the other, trying to get out. And of these, we saw 90% of them saw an increase in travel time, which is to be expected because an evacuation situation like this would indeed provide a lot of congestion, and people would be struggling to get out of the city.
We also ran delay testing, and we compared it against the base condition. With the base condition, the average delay a car experiences finds an equilibrium around 350 seconds, between 5 or 6 minutes. With our extreme scenario, we just have a lot of congestion, large traffic, and that's shown in our delay case here. At the end of an hour, delay for an average car is around 14 minutes. Similarly, with mean speed, longer delays means cars are not traveling as fast. So by the end of an hour, while the base condition reaches a relative equilibrium between 25 and 30 miles an hour, the average car in our extreme condition rounds off at about 12 per hour.
So for deciding what kind of solution we want to implement, we decided to implement contraflow lanes along Highway 101 and Central Expressway. You can see this in our picture here. We have the contraflow heading in the southbound direction. However, we left one lane traveling northbound in case emergency vehicles or law enforcement and such will need to use the highway. And we also implemented new southbound ramps onto Highway 101, as you can see over there. We got this idea from our research looking at a project, similar project done by the South Carolina DOT, where they used this to help implement their contraflow procedures. We also did lane configuration changes at select intersections. One of them is at the bottom of this picture between De La Cruz and Central, where we added additional left turn lanes to help funnel people onto De La Cruz, therefore onto the 101. We also did a travel time analysis for this, and of the affected OD pairs, we saw 63% of them saw a decrease in travel time after the implementation of our lane configuration. Why this number is not higher is because this is still an evacuation type scenario. So you cannot expect even a solution like contraflow to reduce all the traffic down to what it is in the base condition.
Same with the delay and speed comparisons. We also ran a test for the solution scenario. And an important thing to note, similar to the base condition, the solution condition reaches a sort of equilibrium right around 30 minutes. And I mean, cars are experiencing longer delays than the base, but that's to be expected. Rounding off at about 9 minutes, which is an improvement from 14 minutes. Also with the speed, we saw a significant speed increase, averaging out at around 18 miles an hour for an average car, as opposed to 12.
Now I'd like to address some non-technical issues and constraints. Through this developing of this model, we found out that our model is indeed very powerful and very adaptable to different types of problems and in forming solutions for these problems. However, some issues may arise in the actual implementation of these solutions because the implementation of one such as contraflow lanes would take a considerable amount of resources and time. We would need to coordinate with local law enforcement as well as law enforcement from neighboring cities to do things such as set up roadblocks, barricades, etc. to direct people where to go. And implementing these signal retiming plans would also pose problems sometimes because, as Jake said earlier, a lot of these timing plans are under different jurisdictions, so we'd have to coordinate with the city of Santa Clara, the city of San Jose, etc. And some of these signals are also older, so while a lot of these new signals may be able to be retimed electronically from, say, an office, some of these older signals will actually require a traffic engineer to go out into the field and manually change these timing plans.
As far as constraints and flaws of our model, first and foremost, it is a simulation, it is a traffic model, so the results that you see are mainly predictions, but we believe that they're based on reasonable assumptions, based on the data we've collected over the past few months. As far as the current signal timing plans, we've gotten what we could from the city, but it could still be improved and updated. Also, same with OD data. Like I said earlier, we have an old OD table. It's something that can be obtained from the county. They update it every 3 years or so, but the cost to get those numbers is a lot, and we don't have that kind of budget.
So finally, we'd like to end with the closing summary and lessons that we learned. So over the course of the months we worked on this project, we learned that developing a model like this, especially a traffic model of this scale to 100% accuracy is extremely difficult and pretty much near impossible due to all the factors that go into creating a type of model like this as well as driver behavior. We discovered that traffic engineering involves working with a variety of people and organizations, such as our contacts with the city of Santa Clara and the others that assisted us in developing this project. And finally, as Jake said earlier, the results from our simulations are only predictions. So what we can do is just use the data we have as well as the historical data to try and formulate solutions, the best solutions we can to the problems we face.
So in conclusion, we've developed for the city, the county to use what we believe to be an accurate model for the city of Santa Clara. We were able to put this model under different tests, low, medium, and extreme cases, to show how the model can be adapted and used. In the case of emergencies, we noted that there would be trouble if we needed to evacuate the city, but implementing the solutions into our model, we can see the effects of the solutions as well. And the good thing about our model is that it can be continually refined and updated with new signal timing plans, a more accurate OD table, and the best part is that it can be changed basically however the city would want to use it. And given the results that the model can produce, we believe that it can provide viable solutions for the city to use.
So these are just some people we would like to acknowledge who helped us with our project. And thank you for listening. Are there any questions?
This software computer-based kind of model, is it a package? Is it a package that can be used by any city? And
Plotstone Paramex is a British company. Our professor actually introduced this to this project. It comes in like a suite of products. So like any company or the city could just purchase this package of products and use it to hover they desire.
So one program is Modeler, which we use, and then
we also use Analyzer.
Analyzer, which helps